So this little video is about electric motors, which is exciting because we get to talk about not only moving charges and magnetism, of course, uh, but also how they apply in really important ways to our world. All right. Remember your basic symmetry of electromagnetism. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. Right? So we think about that changing flux. That's what creates our current um, in with Lenz's and Faraday's law. And this symmetry is really nicely illustrated when we talk about electric motors and electric generators. So I'm going to spend a little bit of time talking about those because I really like them. And I think they're just a great example of the way magnetism works. So an electric motor uses a current to create a force that turns a rotor. So in, say, an electric car, right, I run a current from my battery through the motor, and that creates a torque that turns the wheels. Okay, so that's our basic setup with an electric motor. And this is, a very simplified picture of one, but it's essentially right. You have a big magnet on the outside, and then you have some kind of wire loop in the middle. This might have, hundreds of wire loops here. We only have one here, but it works in exactly the same way. And the force on this wire is I L B sine phi, um, where that angle is, again, but we called that theta before, the angle between the velocity of the current, that is the direction of the current, I, and the magnetic field vectors. So this leads to a torque around our shaft. Um, and let's take a second to think about that. Um, our torque is going to be equal to uh, the force on the wire times the perpendicular lever arm. So we know that from 151. Our perpendicular lever arm, uh, if our force is on the wire here, is just going to be that distance there between the axis and the wire. And then we want to find the force that's being defined by Lorenz's law. And that torque can then be used to turn a wheel. So let's see how that works in this particular situation. Start with these horizontal wires. Those horizontal wires um, would be complicated to actually figure out our Lorentz force here and our torque. But if you notice, the magnetic field is going left to right. These two wires are both in a horizontal plane. So when they're in the direction of the magnetic field, the current is either going in the direction of that field or going against it. In either case, there's no force because that sine theta that's in the Lorentz force is going to be zero. Okay. In other cases, when it's not directly parallel to those magnetic fields, the force is always going to be perpendicular to the plane. It's going to be straight up or down. So it's not going to create any torque on our axis because it's not acting in around that axis. So we don't really have to worry about this guy and this guy. They get canceled out because of the directions of the forces. So all of the force comes on these two perpendicular stretches, which happily makes our calculations a little easier. When the loop is in line with the magnetic field, that is, when we look at it from the top, and the loop is in this direction, right? So we're looking at the top, the magnetic field's going left to right. In this case, if we think about our Lorentz force, what direction is that going to be in? Well, point your fingers in the direction of the magnetic field and then start over here. Our velocity is going to be up because the current, it tells us, is coming out of the page, and our force is going to be up. Okay. We could do the same thing over here to figure out our force is going to be down. Are these torques in the same direction or different directions? The forces are in different directions, but the torques are in the same direction, right? This guy wants to go around the axis, which is here, like this. This guy wants to go around the axis like that. And so both of them are turning this rotor in a nice clockwise direction. So our torque is actually the force times the width here, which is going to be our perpendicular lever arm, okay, which should be W over 2 for one wire, but when we multiply it by 2, it becomes that whole length. And our torque total becomes the force times the width of that rotor, or the width of our loop. As the loop turns, that torque is reduced, right? Because as we turn here, our torque is going to get smaller because our perpendicular lever arm is getting smaller, if you remember our torque and statics. Okay, so you're not going to get as much torque as the that guy gets straightened out across here. And so we can write how that's going to change. The torque at any given moment is going to be this guy, where theta is how far away we are from being in that ideal perpendicular spot, or ideal parallel spot. And then our force on our wire is defined by this. And essentially what happens as this guy turns and gets to this point, there's not going to be any torque at all. So there's a lot of torque when the rotor or the loop is oriented like this. It gets smaller as it turns, and it turns into 0 when it gets here. So if we want to calculate the full torque all the way around, and we won't go through the math here, but we get this equation. It has to do with the number of loops, the area of the loop, how big the loop is, the amount of current that we're moving through the wire, and the strength of the magnetic field. Like we said before, when we get here, the force is through the axis, so there's no torque. You get an interesting thing that happens when we pass that point, right? If we're rotating this way, once you get here and then move past this point over here, the torque's actually going to reverse, right? It's going to try to turn the rotor that way. If you just let that be, your loop would turn this way and then turn back and turn back, and pretty soon it would just stop in the middle. Okay, so the way that that's fixed is by using what are called brushes to allow that current to change direction. So as soon as it gets to this point, the current will actually change direction, and then the forces will continue to try to move the loop in the same direction. And you can see that it's actually a really nice image here. You can see how as it turns, it would get disconnected and the current would stop, and then it would connect again and the current would go in the opposite direction. And so here's a nice little image of a motor moving. It's moving too fast to really get a good sense of what is happening here. But here you can see the loops of wire here that are being used to create an electromagnet. Then you got more loops of wires in here that are actually turning the motor.